Okay, so this will be a quick run through on the second and third laws of thermodynamics, and both of these deal with entropy. So we talked a lot about entropy in our statistical thermodynamics part of the course, where we were dealing with the partition function in Q, and so we know that it's related to the number of levels that are able to be populated in the system. And if your products have more energy levels able to be populated at that temperature, then entropy is going to drive that reaction forward. And so this is, again, related to heat capacity. And let me just sort of reiterate what I just said in the previous set of notes, that heat capacity is per mole of material. And so for those translation and rotational heat capacities, about 25 joules per Kelvin per mole for polyatomic gases. For water at room temperature, it's 72. So it's higher because we have water molecules moving. So some of those translational motions have been turned into vibrational motions. And so the addition of those vibrational motions now raises that heat capacity. Now, specific heat is per gram of material. And so this, for water, it's roughly 4 joules per gram per Kelvin. And then this delta U, this is a really important equation. We can get the change in internal energy directly from the change in temperature. So we will use this equation a lot over the next several weeks. So since work is 0 with constant volume, the change in temperature with heat input can be used to determine CV. And that's what we were just doing with that calorimetry experiment. Okay. So here's a review of the equations we've covered so far. We've talked about irreversible expansion. So expansion against a constant pressure. So we did this one. We had that conversion from liters atmospheres to joules, using Pascal's conversion from atmospheres to Pascals. We did isothermal reversible expansion, okay, where we had that integration of delta V. And then we also have this at constant volume, delta U is equal to NCV times delta T. Now at constant pressure, this is a way to get the enthalpy. So the CP, the heat capacity at constant pressure, will give us the enthalpy. And that's why we talk about the heat of reaction in our labs and so on. We're using open glassware, so we're actually measuring delta H of our reactions. And then these are what we call the thermodynamic definitions of these functions. It's the instantaneous slope of the internal energy with respect to temperature, keeping volume constant, and the instantaneous slope of enthalpy with respect to temperature at constant pressure. And then this is a very important equation. So let me put some stars on this one. We're going to use this one a lot too. So again, we can take CV and we add another unit of R, or another magnitude or value of R, and get CP. So let's jump into entropy. So this is one of the statements of the second law of thermodynamics. No cyclic process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. And so you might say, but wait a minute, we did isothermal reversible expansion, we calculated the work, and because it was isothermal, delta T was equal to 0. So delta U was 0, and delta U is equal to the heat plus the work. And so if the heat plus the work is 0, then heat has flowed into the system and we did work. It was completely 100% converted into work. And yet this up here says that seems to be impossible. But this is the key right here. No cyclic process is possible. So this is valid for a single leg, but the whole cycle is what we're talking about. So this would be an expansion okay, where this is heat in, Q in, and work out. Then if we were to cool this down, take out some of that excess heat, we could cool it down to this point. There's a couple of ways we could do that. One, we could just let the hot gases escape, like open a valve and let the hot gases escape after we've pushed the crank a little bit. So then we open the exhaust, hot gases leave. So now we put some cool gases in and we compress those cool gases. And we sink the heat. So this is work in, and Q out. So we put some work into the gas, we sink the heat, and then we may catch that gas on fire. And there's a huge jump in temperature. Hot. And we're back up at the initial pressure, initial volume. So do you see how this can run as a cycle? And this is what the second law of thermodynamics is saying is impossible, for this to completely convert all the heat that you put in and get rid of and get the same amount of work out. Those reversible isothermal legs are very efficient, so the heat's being converted into work there, but this cool down and then this compression of the gas is taking some heat out, and we're having to put work in. And so there's never perfect efficiency is another way to say this. So that's what the second law of thermodynamics is preventing. And we're going to see a lot of these cycles, and we're going to do lots of problems with those. So the reason this is impossible is disorder to order or order to disorder is spontaneous. So this is your normal experience with bouncing balls, right? They don't bounce forever. They dampen because the orderly motion is being lost to heat. The ball's heating up, the floor's heating up. We're losing that perfect recoil and bounce to heat. Disorder to order is not impossible, but it's really improbable. Like if something bumped off of this desk, right? Like all of the atoms in the desk have enough energy to bounce this mouse pretty high. But it would be strange if the mouse, if I'm just looking at it and I don't see any of that going on and all those atoms bumped it from the bottom and it bumped up. Okay. It's not impossible mathematically. But to get all of that energy to organize and do that is very improbable. Okay. And so this is I don't know if y'all have ever seen this video from the Jim Carrey movie where he says, "What are my chances?" I don't know if y'all know the scene. He says, "Are my chances not good, like 1 in 100 chance?" And she goes, "I would say more like 1 out of 1,000,000." And he goes, "So you're saying there's a chance?" Right? So just because it's not impossible, I mean, you don't realize how improbable it is. I mean, it's worse than 1 in 1,000,000. You know that all these atoms would bounce this mouse up, and so that's what we're saying. It's not impossible to have order come from disorder, but it's really, really improbable. So improbable we would look for a special cause, right? And so the entropy of an isolated system increases in the course of a spontaneous change. This is another statement of that second law. The simplest isolated system is the universe, and nature as a whole is moving towards disorder. Entropy is increasing, but it's still very low. In fact, this is one of the arguments for the Big Bang of the universe, the big beginning of space and time, because we still have planets, we still have liquids, we still have solids. Remember that the entropy of a gas is way larger than the entropy of a solid or a liquid. So for the universe to not already have expanded to where it's just single particles isolated from each other as a gas, I mean, implies that we're still fairly close to the beginning of the universe. If it were infinite in the past, we wouldn't be here. The planets would have already dispersed, the suns would have all burned out, we would be at thermodynamic heat death. So that's way in the future if things continue to go the way they go, right? So anyway, for a reversible isothermal expansion of an ideal gas, we have this rearrangement, and we can actually calculate the delta S, the change in heat with respect to temperature, okay? And so we get this NR ln at VF over VI. So that's our entropy change for those isothermal expansion legs. And here's now the third law of thermodynamics. So this is all second law stuff. The third law of thermodynamics, at 0 Kelvin, all the excited state energy has been sucked out of a substance. And so the partition function is reduced to 1. We know from statistical thermodynamics that when Q is 1, the natural log of Q is 0. So entropy goes to 0 as the temperature goes to 0. Okay. And so if S is a measurement of disorder, entropy going to 0 as temperature goes to 0, we call that the Nernst heat theorem. And so the third law, this is the way you see it written in the freshman text and other texts. The entropy of a perfect crystalline atomic substance is 0 at T equals 0. But I like the Nernst heat law, or heat theorem, better, and just showing with the partition function that entropy goes to 0 as temperature goes to 0. The practical result is that we have a reference point, and since we have a reference point, we can make standard entropy tables. And so here's our let me just jump ahead to the tables, because that's the point here. So we have these standard entropy tables, and we can look up the standard entropy for all of these substances, whether it be, ammonia gas here, or we could find, hydrogen or oxygen. We could calculate phase changes. So here's water, liquid, entropy. Here's water, gas. We could take the difference and we could calculate the entropy change when you boil water. And so this is a nice result of having that third law of thermodynamics where you have a reference. We also have these standard reaction entropies and enthalpies and Gibbs energies calculated the same way you're very familiar with. So you sum up all of the products, the standard entropies of the products times the number of moles that you have, and then you subtract the standard entropies of the reactants times the number of moles you have for those, and that's how you get your delta S of reaction. You can get the same for the delta H and the same for the delta G. We'll cover those in a later lecture. Now, one thing that's different than those others, if you'll notice, the columns are gray because we haven't talked about them, but let's take hydrogen gas here. The definitions for the enthalpy and Gibbs energy of formation are that it's 0 by definition for the elements in their standard states at 1 atmosphere and room temperature. So those are 0 for hydrogen gas, but notice the entropy is not 0. So that's one place where people make mistakes. They think that definition of elements in their standard states are 0 for all three, for entropy, enthalpy, and Gibbs energy, but they're not for the entropy. Entropy has values because its standard state is 0 Kelvin, and everything else is relative to 0 Kelvin. Okay. All right, so let me go back and just emphasize some of these things here. So we can calculate these entropies, again, using that standard state. We'll go right here and look. We can see that entropy, if we plot it out, we can look at that entropy from absolute 0. It's increasing. We hit the the melting point. So we've got a solid here. It melts, then we have a liquid, then it boils, and then we have a gas. So we can see those phase changes. So here's the calculation of the entropy at any given temperature. You can integrate from 0 Kelvin up to whatever the temperature is. If you're still in the solid state, you have this heat capacity at constant pressure for the solid divided by temperature. And so you would basically integrate this area here, and you would calculate the entropy. Then when you hit that melting point, you have the enthalpy of melting or fusion over that temperature, and so then you would calculate that value. So if you're right here at the beginning of the liquid state at its melting point, then you would stop right there. Let's say you were somewhere in between. If you were right here, then you would have to integrate again that Cp for the liquid. Notice it's a different number because it's the liquid, divided by temperature, from T fusion, the melting point, up to whatever temperature you are. If you're past the boiling point, you would go all the way to the boiling point, and you would calculate it to here. Then you would take into account the vapor pressure, the enthalpy of vaporization, divided by the boiling point. And if you were somewhere here in the gas, then you would calculate from the boiling point up to whatever your final temperature was, using the heat capacity for the gas. And so this is how, let's say this was room temperature for some gaseous substance. This is how we calculate those entropies in the tables. All right. So that's the second law. And next we'll get into cycle problems and applying some of these values, looking at also delta H's and delta G's.